Welcome. Today we're diving into one of the biggest and maybe one of the quietest threats to our entire digital world. We're talking about the quantum deadline. Think of it as a silent clock that's already ticking for your most important secrets, and we're going to figure out exactly what that means for you.
Now, I know what that sounds like. A bit of a scare tactic, right? But it's the simple reality. Right this second, adversaries are scooping up huge amounts of encrypted data. We're talking government secrets, corporate IP, financial records, you name it. And they're not doing it because they can crack it today. They're doing it because they are betting they can crack it tomorrow.
This whole strategy has a name: store now, decrypt later. You can think of it as a massive, silent data heist that's happening in slow motion. The data's locked up, sure, sealed tight with today's best encryption, but the thieves? They're patient. They're just waiting for a brand new kind of key.
And that brings us to our first section here, the coming quantum key. So let's talk about what this master key actually is and why it changes everything. So what is this key? Well, it's a cryptographically relevant quantum computer. It's a machine so powerful it can chew through mathematical problems that are basically impossible for even the world's biggest supercomputers today. And look, this isn't some far-off science fiction. It's a massive engineering challenge that some of the smartest people on the planet are racing to solve right now.
But here's the crucial point. Not all encryption is in the same boat. The huge existential threat is to what we call asymmetric crypto. This is the stuff that handles the digital handshakes and signatures that underpin the internet, the very foundation. A quantum algorithm, Shor's algorithm, just completely shatters it. On the other hand, symmetric crypto, the workhorse that encrypts the data itself, is in better shape. We can pretty much just double the key sizes and stay safe.
So the real bullseye, the primary target, is our public key infrastructure, or PKI. This is the bedrock of digital trust. If PKI crumbles, the whole system of secure communication and e-commerce we rely on every single day goes with it. That's why this isn't just a tech problem, it's a strategic emergency. Which of course leads us to the big question: are you already in trouble? Well, our next section, the quantum readiness formula, gives us a really smart framework to figure that out. This comes from the cryptographer Dr. Mosca, and it's so powerful in its simplicity. It's an inequality. X plus Y is greater than Z. If that equation holds true for you and your organization, well then your data isn't just at risk in the future, it's at risk today.
So let's break this down. X is the shelf life of your data. How many years does this information absolutely have to remain a secret? Y is your migration time. How long will it realistically take you to upgrade all of your systems to be quantum safe? And Z is the big unknown. It's the number of years until a quantum computer that can break today's encryption actually arrives.
Okay, so let's dig into X first, because this number is totally unique to you. It all comes down to one question: how long does your information really truly need to be protected?
For some things, X might be basically zero. Think a temporary communication key. But for financial records, you're probably looking at 10 years or more. What about sensitive medical records or a company's crown jewel intellectual property? Now we're talking 50+ years. And for top secret government data, it could easily be a century. It's simple. The higher your X, the more urgent this problem is for you.
All right, next up is Y, the migration time. Now, this is the one variable we actually have some control over, but it's also the one that's almost always massively underestimated. This isn't just about pushing out a simple software update.
And that's because, as the experts say, this whole migration is significantly harder than it sounds. You're talking about a global upgrade of systems that are deeply, deeply embedded. You've got to hunt down every last piece of crypto in your hardware, your software, your supply chain, and you'll run into nasty surprises like ghost incompatibility, where everything seems to work fine, but it's failing silently in the background. For most big organizations, a realistic migration time is a decade, maybe more.
And that leaves us with Z, the most uncertain and, frankly, the scariest variable of them all. When will a cryptographically relevant quantum computer actually get here? When is QJ?
Well, the honest answer is nobody really knows for sure. As you can see from this table, the expert predictions are kind of all over the map. You've got some saying there's a 1 in 7 chance by 2026. Others are betting on the 2030s, or even pushing it to 2040. And this uncertainty is exactly why just waiting for a definite date is such a dangerous game. The breakthrough could happen way, way faster than most people expect.
So given this ticking clock with an unknown deadline, what in the world are we supposed to do about it? Well, that takes us to our final section, the race for crypto agility. The goal here isn't a single fix, it's about building an adaptive defense. The new toolkit we have is called Post-Quantum Cryptography, or PQC. This is a whole new generation of algorithms built on math problems that are believed to be hard for both classical and quantum computers. But, and this is a really big but, this is not a simple drop-in replacement.
You see, our current classical algorithms have been perfected over decades. They're small, they're fast, they're efficient. The new PQC algorithms, on the other hand, while secure, are much, much larger. And this size difference creates what are called knock-on effects for pretty much everything, from your network performance to the amount of memory on small IoT devices.
And you can see that impact right here in black and white. Look at this. A standard digital signature today is just 64 bytes. Its post-quantum equivalent? Over 3,300 bytes. That is a colossal increase, and a lot of our existing systems just weren't built to handle that kind of load.
And this is exactly why this PQC migration isn't a one-and-done fix. The real goal, the long-term strategic win, is to build a new capability, crypto agility. It's about getting to a place where you can change out your cryptographic algorithms easily, routinely, without having to tear down and rebuild everything from scratch every time a new threat pops up.
So how do we get there without taking huge risks? Well, a lot of organizations are using a hybrid approach. It combines a trusted classical algorithm with one of the new PQC algorithms. It's like a safety net. If, for some reason, the new PQC algorithm has a flaw, you're still protected by the classic one. And if Q-Day suddenly arrives, the PQC layer keeps you safe. It really is the best of both worlds for this messy transition period.
So what should an organization actually be doing right now? The path forward really boils down to a clear, four-step roadmap. First, identify. You have to inventory all of your crypto. You can't protect what you don't know you have. Second, prioritize. Figure out which data has the longest shelf life, your high-X assets, and focus there. Third, migrate. Start a phased rollout, test everything, and begin with your most critical systems. And finally, build for agility. Make this a continuous process, not a one-time project.
And that brings everything full circle, right back to Mosca's simple but incredibly powerful formula. The quantum clock is ticking for all of us, but the deadline is different for everyone. So the only question that really matters now is this: when does X plus Y become greater than Z for you?